Hi, we're gonna start our last chapter, chapter 17. So I'm gonna split this lecture into two because it's a really long chapter and I'll need a break in the middle. So let's, okay. So electrochemistry. So this chapter will tie together everything we've done with equilibrium and tie it into the thermodynamics chapter that we just finished. So this is chapter 18 in the new edition, but it's chapter 17 in your book. And one thing you have to remember how to do is balance redox reactions. So here's a flow chart that you would have seen in Chem 107 for balancing redox reactions using the half reaction method. I'm sure I'll go through a couple of these in my worked problem recording. The important thing to realize in electrochem is we're just taking advantage of reactions that aren't at equilibrium. In the first case, when we're looking at something called the galvanic cell, we're taking advantage of a reaction that's going in one direction in order to do work, electrical work. In the end of the chapter, we're taking advantage of electricity to drive reactions that are that you want to go backwards, so that you want them to go in the opposite direction. So if you put work in, you can force a non-spontaneous process. So we're simply looking at redox reactions, and this is a reminder of how you balance one. So this redox reaction, if you set it up right, could be used to make electrical work as it goes towards equilibrium. So the dichromate plus chloride going to the chromium 3 or 3 plus and chlorine gas is a redox reaction. So we'll see that when we go through the balancing process. So the first thing that we're going to do to balance it is split it into the two unbalanced half reactions. That really just says separate it into the different ions. So chromium has to go to chromium, chlorine has to go to chlorine. So we have those two half reactions. Both, now we're going to balance them both for everything except the oxygen and hydrogen. So I hope you all have done this in Gen Chem 1. So in the first half reaction, dichromate has two chromiums within that polyatomic ion. And so we have to form two Cr3 plus. And in the second case, chlorine gas on the product side is diatomic. So we have to have two chlorides in order to make the atoms equal. After you do that, we know that it's in a solution. So in each of these cases, we're using the subscript aqueous. So we know that we're in water. Water can be part of our reaction. We're going to need another source of hydrogen. So in all cases, you'll start by assuming it's in acid, which we'll call H+. And then we'll take into account later whether or not it might be in a base. So all the atoms are balanced except the oxygen and hydrogen. And what we had was dichromate was 7 oxygens on the reactant side. So that means we have to make 7 waters in order to get the element oxygen to balance. Once you add 7 waters to the product side, then you need 14 H pluses on the reactant side in order to get the hydrogen and the oxygen balanced. In the second reaction or half reaction, there is no oxygen or hydrogen, so this step isn't necessary. The next thing is to look at what's being oxidized and reduced and add electrons. So when we look back here, we have on the reactant side 14 times +1 and then -2, so we have +12. On the product side, we have +6. And so in order to get them to balance, the only thing we have left we can add is electrons because the elements are all balanced. So to balance a +12 with a +6, we have to add 6 electrons to the reactant side. And in the second case, we have to add 2 electrons to the product side because we have two chlorides, each with one extra electron. And on the product side, they're both neutral chlorines. So we'll add 2 to that side. So this is just what I just talked through. And now you notice that both sides are balanced for all the elements and for charge. So it's a little more complicated than just balancing for the elements. Before we add them together, though, we have to know that if this reaction's taking place, the reduction process, which is consuming electrons, notice in reduction, the electrons are reactants, and in the products, or in the oxidation half reaction, electrons are products. If you're having a reaction take place, you have to have equal number of electrons gained by something as the other half reaction is giving up. So if the chloride reacts to form chlorine, it has to give up enough electrons for the quantity of dichromate that is gaining those electrons. So we're going to multiply the oxidation reaction by 3, and therefore we'll have 6 electrons gained in the reduction and 6 lost in the oxidation. So we'll do that multiplication, and when you add it up, first thing you'll notice is the electrons have to cancel. You can't have electrons coming in from nowhere or going to nowhere. They're being exchanged by different chemicals, but they're not coming and leaving the system. And so we end up where you can check and make sure you're correct. If you can balance the elements on each side, so if you have 14 hydrogens, 2 chromium, 2 chromium, 7 oxygen, 7 oxygen, 6 chlorine, 6 chlorine, they're balanced. And then you also have to make sure the charge is balanced. So we have +6 on the reactant side, +6 on the product side. So you can always make sure that you've balanced your redox correctly. So the thing about electrochem is we're taking advantage of a reaction like this, but we're not just mixing the dichromate and the chloride. We're not letting them come up against each other and exchange electrons. We're forcing those electrons to go through an external circuit. So in electrochemistry, it's a chemistry that concerns the interconversion of chemical and electrical energy. So if a reaction wants to go to equilibrium and it's spontaneous, which we discussed in the last chapter, then you can take that desire for the chemistry to change and make it into electrical energy if you set it up right. So essentially we have to build a machine. So a galvanic cell or voltaic is a spontaneous chemical reaction that generates an electric current. So we're going to go through this in great detail. An electrolytic cell is using electrical current to drive a reaction that isn't spontaneous. And the reason you'd want to do that is to make some highly reactive species that isn't present in the environment. So for a galvanic cell, we could mix chunks of solid zinc and Cu2+ in an aqueous solution, and it would react to make zinc 2+ and copper. And if we did that in just a beaker, the exchange of electrons would be random and we wouldn't be able to do any work. But if we look at what these half reactions are and notice that zinc is giving up electrons that copper wants, the first picture is just showing you doing this reaction in a beaker. So you do it in a beaker, the reaction takes place, the solution starts to turn color. I feel like it should turn color the other way, but maybe zinc is blue, copper is a more green color. This is just showing you as time goes on, you're going to start coating the surface of the zinc. So what we put in this flask was zinc solid into a Cu2+ aqueous solution. As the reaction goes on, the zinc metal goes into solution as zinc 2+, and the copper becomes solid, so it coats the surface of that chunk of metal. So the way we set it up here, you couldn't get any work out of it. The electrons are being exchanged in random directions. If we set it up in an electrochemical system, call it a galvanic cell because the reaction will go towards equilibrium in the forward direction. What we're going to do is set it up so that the oxidation and the reduction half of the reaction take place in separate places, so that the only way for electrons to get from one to the other is to go through a wire that connects the two. So we put on the right-hand side the zinc solid, and it's in a solution of zinc 2+, and electrons are going to leave that side of our electrochemical cell. They're going to go over to the Cu2+, which wants to pick up the electrons. So the copper 2+ wants those electrons. It's spontaneous for this reaction to take place. But now we're forcing the electrons to go through an external circuit. And when you do that, you can use some of that kinetic energy of the electrons to do work, such as light a light bulb, charge your battery. So each of these metal surfaces is absolutely essential, not only for the chemistry in this case. We need solid zinc and we need solid copper, but we also just need something that conducts electricity, something that will carry electrons out of the solution up into the wire. As soon as one electron goes from the right to the left, now you have charge imbalance. You have more positive on the right, more negative on the left. And that just doesn't happen in nature. Positive and negative attract each other. So the only way to keep the charge neutral is to have something like a salt bridge. There are other ways with membranes that we'll talk about in fuel cells and things, but in this system, the best way is to connect it in that salt bridge. It's like a jello consistency, and you dissolve some ions in there that will move quickly but won't undergo reaction. So in this case, we have sodium sulfate in our salt bridge. As the charge becomes more negative on the left-hand side, the cations can flow into the solution and balance that charge. And on the other side, if it's losing electrons and becoming more positive, then the sulfate ions can leave the salt bridge to balance that charge. So the salt bridge essentially closes the circuit, makes it so that electrons can move by not allowing that electron motion to build up a charge difference. So we need to learn some new terminology. And the first is, what's the anode? So the anode is the electrode where the oxidation occurs. So if we go back here, oxidation is the loss of electrons. So the anode was the chunk of zinc. That's the electrode where electrons are lost. The electrode where electrons are produced is what anions migrate towards, and it has a negative charge. So anions migrate towards the anode because electrons are leaving that side of the cell and going to the other one. So we're losing negative charge in that case. So the cathode is just the other electrode. There'll be the left-hand side where reduction occurs. The electrode where electrons are consumed. So when we look at that chemistry, they're used by the copper 2+ to make Cu solid. The cations migrate that way, and it has a positive charge. So why do negative ions move towards the negative anode? So this is just showing you that if this is the anode, where you have loss of electrons, then as the zinc moves up to the electrode, if it, as the zinc solid electrode loses electrons, it puts a positive cation into solution, and therefore a negative ion is going to move to that surface to balance the charge. So take a little break right now and do 17.1, where you just have to sketch a cell. So you have to sketch something like this. How do you set up the chemistry in order to get work out of your cell? So take a little break and do 17.1. So for our galvanic cell, now that you're back, hopefully you have a little better feel for all of the components of the cell. The anode half reaction is where the electrons are lost, cathode where they're gained. So essentially electrons are products on the anode half reaction, reactants on the cathode. When you add them together, that's why we had to remember how to balance redox. all the electrons have to go away. So we have to balance them in quantities that make the electrons equal. And it's a lot of work to either write out the whole schematic of the cell or to write the whole reaction. So the shorthand notation for a galvanic cell is the notation on this slide, where you start with the anode on the left and write the cathode chemistry on the right. And phase boundaries are represented by lines like this. And the salt bridge is represented by a double line and then another phase boundary. So if you think about it, when you look at this, our zinc chunk of metal was dipped into a solution that had zinc 2+ in it. So that's a phase boundary. That's a solid chunk of metal stuck into an aqueous solution. Then what connects that to the other side, the other chemistry, is a salt bridge. And there are essentially two phase boundaries. There's a phase boundary on this side between this solution and the salt bridge, and then there's a phase boundary on this side between the solution and the salt bridge. So the shorthand notation has a double vertical line for a salt bridge, and then we give the other chemistry. So notice if we go anode cathode, the chemistry makes sense. It's zinc solid as a reactant going to zinc 2+, and the other half reaction is Cu2+ going to copper solid. So this direction for the shorthand represents the chemistry of our cell. So before you go on to this slide, take another little break and do problem 17.3. So another problem within the reading, so that you understand for sure how to do that shorthand notation, because that's going to be the best way to represent the chemistry in a galvanic cell. So you'll see that a lot. So once the cell is created, then we want to think about how we get electricity out of it. So the cell will have a potential. And what you really want to think about is there's a desire for electrons to move. So if we go back to this reaction, all we're saying is this reaction goes spontaneously forward, that its equilibrium constant is bigger than Q. So it's going to go forward in the direction to make those two equal. So as it goes forward, there's a desire. So that's really what the potential is. A desire for electrons to move from one chemical species to another. So the electromotive force, EMF, the force or electrical potential that pushes the negatively charged electrons away from the anode and pulls them towards the cathode. It's also called the cell potential or the cell voltage. I'll usually use cell potential. All of them are given the symbol E, and it's measured in units of voltage. So you want to think about the potential as the tendency or the desire for something to happen. So I like to think of this as water at the top of Pikes Peak. So there's a potential, if that water were to come down Pikes Peak, that you could do some work. You could turn a paddle and grind some wheat, or you could turn a paddle and make electricity. So the voltage is like the difference in altitude for water. The coulombs, or the amount of charge that actually moves, is like the water. Once water moves from the top to the bottom, then you get work out. But when it's just sitting there, it's just a potential. So that would be like the voltage. So we have cell potential measured in voltage. So the capital V is for volts. And if we allow electrons to move through that potential difference, we get work. So work will have units of joules in this case. So 1 coulomb of charge flowing through 1 potential difference of cell potential gives us a unit of 1 joule. So we want to now think about how this relates to a free energy change, because we know a free energy change tells us the direction for a spontaneous reaction. And this slide has a typo in it. This D right here should be a delta, and this D right here should be a delta. So delta G is related to the cell potential, which makes a lot of sense. If a cell has a positive potential, the chemistry wants to go forward. And we know that should mean the reaction has a negative delta G. So delta G equals negative, N is the number of moles of electrons that are transferred. Faraday's constant F just relates the charge in units of coulombs to the charge on an electron, and then E is the cell potential. So this tells you that a positive cell potential gives you a negative delta G. So that's the same thing as saying that if I get a positive potential in my cell that I set up, the reaction is spontaneous because delta G is negative. You could also think of that as under standard conditions. So a delta G, remembering the D is a typo, under standard state conditions is equal to negative NFE, the cell potential at standard conditions. So we will just look at using the standard cell potential. So here's the reaction that we've used as an example. And it tells us that this cell has a potential of 1.10 volts for this reaction when we're at 25 degrees. And you know that equilibrium constants change with temperature and delta G's change with temperature. So we need to know the temperature in order to relate the cell potential back to the delta G. They want us just to calculate from that the standard free energy change for this reaction at 25 degrees. So we have to look at the reaction first and decide how many electrons were transferred. This is a pretty easy one. Copper 2+ going to copper neutral means there are 2 electrons transferred. Zinc has to have the same amount, but we could check. Zinc going from 0 to zinc 2+ is the process of giving up 2 electrons. So there's a 2 electron exchange. So we have 2 electrons and Faraday's constant, which is in your table of constants. And we have voltage. And yeah, so we have coulombs and volts. We know 1 joule is 1 coulomb per volt, and we'll change it into kilojoules just because it's going to be a big number. So a cell that has a plus 1.10 volts for its cell potential under standard conditions has a delta G under standard conditions of negative 212 kilojoules. So that makes sense. The cell potential is positive. You get an electric current as this reaction takes place. That means you're taking advantage of a spontaneous reaction and the delta G is negative. So when we look at using tables, we have in this case, okay, so this is the reaction of hydrogen gas to make H+. And if you have 2 hydrogens doing that, you're giving up 2 electrons. The other half reaction is the copper one where it's picking up electrons. And so the standard potential of a cell is just the sum of the standard half potentials for the oxidation at the anode and the reduction at the cathode. So by definition, we will give this one a cell potential of 0 because you can't really measure the cell potential of a half of a cell. But if we set the hydrogen electrode, so this first anode reaction, to have a cell potential of 0, then we measure everything relative to that. Then we'll be able to then take those values and look at them relative to each other. So in this case, the anode half reaction, we're going to say is 0. The reduction half reaction, therefore, has the entire cell potential, and it's 0.34. Okay, so this is just talking about that electrode. The standard hydrogen electrode has been chosen to be the reference one, which is what I just mentioned, so that when we have on the right-hand side, the standard hydrogen electrode, we're pumping hydrogen gas in so it can react. And here's the H+ in solution. Electrons are flowing away as the hydrogen gas comes in to make the H+. So it's the oxidation half. So it's a piece of platinum foil. So because if we look at this reaction, the first anode reaction, None of those are metals, so they can't carry electricity. Whereas in the second case, copper is a metal. So when we make the hydrogen electrode, we have to have some electrode that will carry electrons away that won't react. So it's usually a piece of platinum, because platinum is very non-reactive. So this is platinum. We're bubbling hydrogen in. It reacts to make H+, and then the electrons flow this way over to whatever other electrode we have over there. Okay, so that's been chosen as the reference. So we say that under standard conditions, so where H+ is 1 molar, the hydrogen gas is 1 atmosphere, and it wouldn't matter which way you're going, they'd be both 0. So whether or not it's the oxidation in your cell as you set it up, or the reduction, we'll set that to be 0. And so in this case, when we look at the reaction we looked at a little bit earlier, that means that if the cell's measured potential is 0.34 and one of the half reactions is the hydrogen electrode, then now we can say that the copper picking up electrons has a reduction potential of 0.34. So this is just a picture of how you would measure that. So this is another system. You can now put the hydrogen electrode next to the zinc half reaction and measure that to be 0.76. Therefore, if we say the hydrogen is 0, the zinc in this case is undergoing oxidation. So the reduction potential for zinc is negative. So we'll talk about that right here. So in this situation, so back here, we set it up so that the copper was being reduced and the hydrogen was being oxidized. Now we have a system where it's the opposite. The zinc is being oxidized and the hydrogen's being reduced. So now when we measure the cell potential for that, we get the cell potential, we measure it to be 0.76. So that's what your digital voltmeter here is doing. And you're gonna use voltmeters when you work with some fuel cells the last week of the class. So, but this is the potential for the zinc to be oxidized. And when you look at the tables, they're all standard reduction potentials. So we want to put in the table the potential for the reduction of zinc. So it's just going to be the negative for when you compare it to its potential for oxidation. So in the table, you will find a standard reduction potential of negative 0.76, because when you measured it here, zinc was being oxidized. So this is just a table. It's a short one. At the back of your book, you have a much, much longer table with lots and lots of standard reduction potentials. So notice these are each for something gaining electrons. So it's a reduction potential. So when we use these, we have to think about the sign. So if the cell we're creating is this first one, zinc solid plus copper 2+, then the copper is being reduced. So we take its value right out of the table. But the way we set up our cell, the zinc is being oxidized. So we're going to take out of the table the negative 0.76, but we have to change the sign because in our cell, we're choosing this to be an oxidation process. So you have to change the sign from reduction to oxidation if that's how your cell's set up. So you get an E0 of 1.10 for that cell. The next one, notice it's silver being reduced. So this will come right out of the table, 0.80, but copper is being oxidized. So when we look back, see if copper is in there. Yeah, copper is in there. Its reduction potential is 0.34 right there. And so we had to change the sign because we're choosing a reaction where copper is being oxidized. Notice that when I multiplied this by 2, because I needed to get the electrons equal, I did not change this value. So let's look at silver in our table. Silver is right here. its reduction potential is 0.80, so towards the top of the table, about a third of the way down. And even though I multiplied it by 2, I don't multiply the standard potential by 2, because a potential is not a quantity. It's the desire for something to happen, the tendency. So it's an intensive property. It's not dependent on the quantity. Okay, so I'm going to have you stop here and do problem 17.8, where you just look up E zeros out of the table. And then I will come back with the second half of this lecture and talk about the Nernst equation.